Dear students, till now we discussed basics of the subject, the Boolean algebra, various operators, basic operators, derived operators, and few of the relations which are possible on the basic operators, relations which are possible on XOR, XNOR, and we discuss the universal logic gates. We did few problems based on the theory what we discussed, simplification of the Boolean functions, equations using properties, and implementation of the given Boolean function, few of the functions using minimum number of 2 input NAND gates, minimum number of 2 input NOR gates. Of course, we emphasize how we are implementing particularly exclusive OR, exclusive NOR with a minimum number of 2 input NAND gates, with a minimum number of 2 input NOR gates. And also, we discuss neutral function, what are the means of the neutral function, what are the means of self-dual function, and we discuss when a neutral function is possible to be a self-dual function, and we identified the number of self-dual functions are always coming as a subset of the neutral functions. So neutral functions are superset. So these are the various things what we discussed till now. Of course, with this, the Boolean algebra, this topic is not completed. We have to do few more things with the Boolean algebra, particularly K-maps related work we need to do. So before starting the K-map, let us discuss the number system. In the first class, beginning class, I mentioned in the beginning session, I mentioned what order we are following the syllabus to cover. So after this basic part, I said we'll be discussing the number system. So let us see now the number system. Suppose consider we are having a number with digits d and -1, d and -2, and so on, d1, d0, with the base, the radix as r. When we are having a given number with the so many digits, dn -1, dn -2, and so on, d0, the leftmost digit must be named as most significant digit. It must be named as most significant digit. We are giving here more generic names. The rightmost digit must be named as least significant digit. Whenever the given number is having the base, that is the radix, which is not equal to 10, for such number, generally we are interested, look, what is its equivalent decimal value? Say for example, we are having a given number, the base of say 7. So generally we are interested, what is its equivalent decimal value? So to read its equivalent decimal value, whenever we are having a radix which is not equal to decimal 10, we are using a polynomial equation. The polynomial equation is r to the power of n-1 dn -1 plus r to the power of n-2 dn -2 and so on, r to the power of 1 d1 plus r to the power of 0 d0. While evaluating this polynomial equation, we are reading its equivalent decimal value. Say for example, we are having a given number as say 2, 3, 4, which is having the base as 7. For this number, if at all we are having the interest to look what is its equivalent decimal value, then based on this we are looking here, this digit is d2, this is the d1, this is d0, so that this is the most significant digit. We are looking here, If the d suffix is n minus 1, the radix power is n minus 1. If the d suffix is n minus 2, the radix power is n minus 2, and so on. It is observation what we are having. Based on this, we are looking here while evaluating this suffix for this digit is 2, so that 2 into or 7 to the power of 2 into this d2. 7 to the power of 1, because d suffix is 1, into 3. 7 plus 7 to the power of 0 into 4. While evaluating this, we are having its equivalent decimal value. If you work out well, so this is coming to be 98. 7 7 ja 49. 49 to 2, 98. 7 3 ja 21. 7 to the power of 0 is 1, so that it is 4. So we are looking here, while adding this, the equivalent value is coming to be, verify, 98 plus 21 plus 4, 123. Check if any numerical mistake is there, verify. The answer is 123. Okay, so like this, we are having the evaluation, or we are trying to look to the result of equivalent decimal value whenever we are having a given number which is having the base, that is a radix, which is not equal to 7. We are looking here, this number is a pure integer value we considered. But in a practical situation, it may be the case the number may not be always only the integer value. It may be consisting of even the fractional value. It may be consisting of the decimal value. It may be consisting of decimal value. So the given number may not be always pure integer. It may be a mixed number, some integer part, some fractional part we may be having. If that is the situation, the number we must write as radix point d minus 1, d minus 2, and so on, the radix r. If that is the case, the equivalent decimal value, if you read, for integer part is concerned, we are looking to the same equation. Coming to the polynomial, coming to the fractional part, it is also same. So plus d suffix is minus 1, so radix power must be minus 1, d minus 1. D suffix for next digit is minus 2, so r to the power of minus 2, d minus 2, and so on. So while evaluating this, we are reading the equivalent decimal value with this decimal point. We are reading the equivalent decimal value with a decimal point. It is possible to build the number system taking the radix may be any decimal number. It is possible to build the number system. Of course, we are familiar with a few of the standard number systems. It is possible to build the number system taking the radix may be say 10, or radix may be say 16, the radix may be 8, the radix may be 4, the radix may be 2, the radix may be 5, the radix may be 6, the radix may be 12. While taking any decimal number as a base, it is possible to build the number system. And of course, whenever we are having the base as 10, we are naming this as decimal number system. When the radix is 16, the number system is named as hexadecimal number system. When the radix is 8, the number system must be named as octal number system. When the radix is 4, the number system must be named as nibble number system. The radix is true, it must be named as binary number system, and so on. So in fact, these are the few standard number systems we are having a familiarity. Most of the times we are having the questions. The questions are possible most of the times as while giving some number, decimal number, while giving some decimal number, we are having a question. What is its equivalent hexadecimal? What is its equivalent octal? And so on in general. What is the equivalent nibble number? What is equivalent binary number? What is its equivalent radix 5 number? Like this, we are looking to the questions most of the times. There is a possible questions in the multiple choice, or maybe sometimes is a fill in the blank numerical questions. These are the basically possible objective type questions. When we are looking the decimal number, some in this given example we are looking some part is integer part, some part is a fractional part. The conversion work for integer part and conversion work and the fractional part of the given decimal number is not same. There is small difference in the conversion work of this integer part and fractional part of the decimal number. So let's look how we are having conversion. Suppose, let us concentrate first the integer part. This integer number, when we want to read as equivalent to radix or number, the work what we are having is the given integer number or integer part of the number. Integer number or integer part of the number. Sometimes maybe pure integer only may be given. Sometimes maybe it may be like this, a mixed number, some part is integer part, some part may be fractional part. So this integer part of the number, to read its equal to radix or number, the work what we are having is this given number is divided with the base, is divided with the radix. So we are having first division. With this, we are looking some coefficient value, some remainder. Later we are checking whether this coefficient is less than the radix value we are checking. If coefficient is less than the radix value, if this is yes, no further division is possible. No further division is possible. But if Q1 is not less than the radix, then further division is possible. Further division is possible. So it is a work which is involving to convert the integer part of the given decimal number as equivalent to its radix or number. Suppose consider the coefficient is not less than the radix, then we are looking here further division. Second division, so it is a coefficient Q2, radix R2. So until this condition is true, we are go on dividing. So consider it is a QL, assume QL is less than the radix, and this is the last coefficient, last remainder. From this, its equivalent number, that is the radix or number, will be Q last, radix last, and so on R1. This is the equivalent radix or number for the given decimal number integer part. So we are having the last coefficient is the most significant bit. Last coefficient is the most significant bit of the radix or number, and the first remainder is the least significant digit. So this is the work which is involving. The discussion what I did here, which is generic procedure I mentioned. Now this work possible to extend to convert the given decimal number integer part to any other number with the radix of any value. Let us try first to the equivalent hexadecimal part. So whenever radix is 16, as I said, it is an hexadecimal number. So 17 must be divided with the radix 16. So 16 4 the 64. The remainder is 7. 64. 16 4 the 64. The remainder is 7. Hence, we are looking here, coefficient is smaller value than the radix. Further division is not possible. The equivalent decimal, the decimal 71 equivalent radix 16 number will be this. Hence, we are looking here, it is 47. And similarly, let us try for octal, nibble, as well as so and so what I mentioned here. Equivalent octal number to read, this number must be divided with the radix 8. 8 8 is 64. The remainder is, of course, 7. This is not less than the radix. As and when the coefficient is not less than the radix, as and when coefficient is not less than the radix, we are having here the further division, 8 1 8. So the remainder is 0. Hence the number is 107. It is the equivalent octal number for decimal 71. Similarly, equivalent nibble number, it must be divided with 4. So 4 1 4. 4 7 28. The remainder is 3. Verify if anything going wrong, numerical calculation, if it all going wrong, tell me and check yourself, modify yourself. 4 1 4 and of course 3. So 4 7 28. The remainder is 3. Okay. The coefficients not smaller value in the radix, we are having a further division. 4 4 16. The remainder is 1. It is not smaller value in the radix, so further division. 4 1 4. The remainder is 0. Hence it is 1013. It is 1013. Similarly, equivalent binary number, it is to be divided with the radix 2. That is binary number, base is 2. 2 3 6. 2 5 10. Remainder is 1. 2 1 2. 2 7 14. Remainder 1. 2 8 16. The remainder 1. Coefficient is not smaller value than the radix. Once the coefficient is not smaller value than the radix, we are go on dividing. 2 4 8. Remainder 0. 2 2 4. The remainder 0. Coefficient not smaller, so we are going further division. 2 1 2. The remainder 0. So that this must be named as least significant bit. This must be most significant bit. The word bit we are using only for the binary number system. In all other cases, in all other number system, we are using a word as a digit. We are using a word as a digit. Bit is a word we are using only for binary number system. The reason is, in the case of the binary number system, the discretes are only 2, 0 and 1. It's a reason to name bit. So we are looking here, the number is 100111. 1000 111. It is equivalent binary number. Similarly, the equivalent radix 5 number, let us try. So it must be divided with 5. 5 1 ja 5, 5 4 ja 20, the remainder is 1. Coefficient not smaller value than the radix, further division is possible. 5 2 ja 10, the remainder is 4. Coefficient is smaller value than the radix, further division is not possible. So number is 241. So that it is a general procedure to convert the integer part of the given number as equivalent radix or number, as equivalent radix or number. Now let us come to the conversion of the fractional part of the number as equivalent radix or number. For the given number, the fractional part we are having is this 0.16. To read its equivalent radix or number, the procedure what we are having is the fractional part of the given number. Now it is multiplied with the radix r. Now it is multiplied with the radix r. In the integer part case, it was divided. Now here it is a multiplication. While doing the multiplication, we are having some integer part and some fractional part. Some integer part and some fractional part. What is the integer part we are reading? After this radix point, the first digit is this integer digit. This integer digit is the first digit after radix point. Later we are looking f1 value. If f1 is 0, if f1 is 0, that is coming to be true, further multiplication is not possible. Further multiplication is not possible. But if f1 is non-zero, further multiplication is possible. Further multiplication is possible. So, assuming this f1 is not equal to 0, if it is the case, then we are having a further multiplication. The multiplication is only to the fractional part, only to the f1, only to the f1. So when we are having this further multiplication, integer part is not taken into account, or integer part is to be assumed as a 0. So further multiplication we are having only on the fractional part. While having multiplication here, we are having, say, some integer digit and some fractional part. So we are looking now after this radix point, the second digit, after radix point, the second digit is I2. Second digit is I2. And so on like this. It is to be continued. And so on like this, it must be continued in the normal situation until the fractional part becomes 0. In the normal scenario, it is to be continued until the fractional part becomes 0. But of course, we know it may not be guarantee always with the multiplication, the fractional part is resulting to be 0. With any number of multiplications, there may be a situation the fractional part never becomes 0. In that situation, the question arises when to stop. The question arises when to stop. The answer to this question is, if at all we are looking to the further multiplication, if we are having the further multiplication, if the same digit is repeating at the integer plate, at the in the integer part, in that case we are stopping further multiplication. That is one approach. But in general, I am talking where to stop, when to stop. That is basically based on our usage, based on our need, based on our application. If we are looking to the more critical application, more critical scientific application, suppose vehicle launching, rocket launching, something like this, then definitely we need to have more accurate value. If you want to read the more accurate value, we need to do more multiplications. The observation what we are having here is, each multiplication is producing one digit after this radix point. Each multiplication is producing one digit after this radix point. If we want more accurate value, then definitely we need to go for more multiplications. But suppose we are having simple financial application, for example, then maybe after the radix point 2 or 3 digits may be enough. In that case, we are stopping after these 2 or 3 multiplications. So basically, when to stop, where to stop, the question will arise if the fractional part never becomes 0 with any number of multiplications, based on our need, based on our application, based on our usage. Let us come to this example now. Let us start again the conversion work with the hexadecimal case. This number we want to read as equivalent hexadecimal number. So multiplication we are having with radix, that is 16. So 16 while multiplying, it is 2.56. Hence, after this hexadecimal digit, after this hexadecimal point, we suppose name this as hexadecimal point. Don't name as decimal point. The word decimal point we are using whenever the number is with the base of 10. When the number is with the radix of 16, it's supposed to be named as hexadecimal point. It's the thing what I said in the general case also. I given the name here, this as the radix point. This I named as radix point. So it's a more general way of speaking. So that after this hexadecimal point, the first digit must be 2. The fractional part f1, based on the notations what we are using here in the general case, the fractional part f1 is not equal to 0. Because of this, we are having possibility further multiplication. So further multiplication, as I said, only on this fractional part. When we are having further multiplication on this fractional part, this is resulting as, I think, it will result as 8.76. I can check. I think it is 8.96. 8.96. So this is 8.96. So second digit after this hexadecimal point is 8. The fractional part f2, based on the notation what we said, is not equal to 0. So further multiplication we need to proceed. So if you do this, I think this is 15.96 into 16. 15.36. 15.36. So the third digit will be F. In the hexadecimal number system, this decimal 15 is represented as F. In the case of the decimal number system, the discretes 0, 1, 2, and so on 7. In the case of hexadecimal number system, the discretes 0, 1, 2, and so on 7. Later, for representing this decimal 10 to decimal 15, we are having the usage of these symbols A, B, C, D, E, and F. So, from decimal 10 to decimal 15, we are representing with these symbols, and so on. F is 15. Similarly, when we are having the number system, the base of 8, the discretes will be 0 to. So when we are having a number system with a base of 8, the discretes are 0, 1, 2, and so on 7. The number system is Nibble number system, then discretes 0, 1, 2, and 3. The number system is a binary number system. In that case, of course, the discretes 0 and 1. So based on this, of course, I mentioned here, the hexadecimal case, 15 is F. So like this, we are working. Here, if you go any further multiplication, it seems to be the fractional part never becomes 0. So let's stop with this 3 digits after hexadecimal point. So after hexadecimal point, we must write point, that is hexadecimal point 2, 8, and F. 2, 8, and F. So similar work we need to extend as per the need what we are looking here for octal, nibble, binary, and also radix 5 number. So to read the equivalent octal number, it is to be multiplied with the 8. When it is multiplied with the 8, it is 1.28. Hence, after octal point, the first digit is 1. Into 8, the multiplication is only to the fractional part. 0.28 into 8, it is resulting as 224, so 2.24. So second digit is 2. Fractional part not equal to 0. We are having further multiplication. This multiplication is giving 1.96. So it is 1. If it seems here also, if you go for any number of multiplications, the fractional part never becomes 0. Let us stop here also after these 3 digits. Hence, the equivalent octal number for this 0.16 decimal number is 121. Equal nibble number, if you look, 0.64. Fractional part not equal to 0. We are going further multiplication. If we are having a multiplication, it is 2.56. So 2.56. The fractional part not equal to 0, we are looking further multiplication. So 2.24. It seems here also if we do any number of multiplication, the fractional part never becomes 0. Because of this equivalent nibble number after nibble point, it is 0.022. Similarly, let us come to the binary equivalent. If you look to the binary equivalent, it is to be multiplied with the 2. So 0.32, fractional part not equal to 0, we are looking further multiplication. 0.64, fractional part not equal to 0, so we are looking further multiplication. 1.28, fractional part not equal to 0, we are looking further multiplication. 0.56, not equal to 0, we are looking further multiplication. 1.12. It seems here also same thing. If you do any number of multiplications, the fractional part never becomes 0. So let's stop here. After this, I think we did 5 multiplications. After these 5 multiplications, let us stop here, so that it is binary point 00101. Binary point 00101. Let us try similarly for equivalent radix 5 number. The equivalent radix 5 number, the number 0.16 must be multiplied with the 5. So this is 0.80. After this radix point, the first digit is 0 into 5, 4.00. So after this radix point, the second digit is 4. Because the fraction part is 0, as per this notation, f2 is 0 after 2 multiplication. Because the fraction part is 0, we are reading no further multiplication. We are not having any further multiplication. In fact, this is exact equivalent decimal 0.16. This radix 5 is exact equivalent to the decimal 0.16. In all other cases, we are looking here, we are terminating the multiplication after few multiplications, because we are looking fractional part with any number of multiplication not resulting to be 0. Because of this, we terminated after few multiplication, but it is not the case here. Just after 2 multiplications, the fractional part is 0, hence we forced to stop. Then it becomes the equivalent exact radix 5 number 0.04. So what we are understanding, particularly for the fractional part is concerned, each multiplication is basically producing one digit. To read 3 digits, in the case of this hexadecimal, we did the 3 multiplications. You can see the work. Here, to read the 3 digits, 3 multiplications. Here, same thing. Coming to this binary, to read 5 bits, we did 5 multiplications. So each multiplication is producing one digit in general. I am talking after the radix point. It is a work which is involving. It is a work which is present here. So this is the generalized procedure for converting the given decimal number as equivalent to radix or number. Most of the times, we'll be having questions, particularly in the GATE papers or any objective type question papers. The questions what we'll be looking is, some binary number may be given. Say for example, I am referring to the same example. This binary number 1000111 binary point 00101 is given, and we'll be having a question, what is its equivalent hexadecimal number? What is its equivalent octal number? What is its equivalent nibble number? These are the very regular, very common questions. Whenever we are having the given number in the binary number, given number is in the binary number, the conversion this binary number to hexadecimal or octal or nibble is a little simple work. The procedural work is concerned for converting the binary number as equivalent hexadecimal or octal or nibble number. The procedural work is concerned, it is the same. The procedural work what we are having here is grouping of the bits. The procedural work what we are having is grouping of the bits. What way they are differ if you look? The differ is in the group size. The differ is in the group size. The binary number when we want to convert as equivalent hexadecimal number, the group size is 4 bits. The binary number we want to read as equivalent octal number, the group size is 3 bits. The binary number when we want to convert as equivalent nibble number, the group size is 2 bits. So procedural work is same. The procedural work what we are talking is grouping of the bits. The difference what we are having is in the group size. So let's try first its equivalent hexadecimal number. The integer part is concerned, the grouping will start from the least significant bit of the integer part. So as I said, group size is 4 bits. We are having 2 groups on this example. For each group we must read its equivalent hexadecimal number. The hexadecimal number for this is 70111. For this binary equivalent hexadecimal number is 7. For this is 4. So that this is 47. 47. And of course, in the second group we are having only 3 bits. For your convenience, if you want, you can prefix 0. For your convenience, if you want, you can prefix 0. Group size is 4 bits. For your convenience, if you want, you can prefix 0. So whether we are prefixing 0 or not, effectively the numerical value is not affecting. Similar work, let us extend for octal and nibble. For octal, the group size is, I'm talking first integer part. Octal, the group size, I said 3 bits. So we are looking here 3 groups. For each group, as usual, we must read its equivalent octal number, octal digit. This is 7, this is 0, this is 1. Hence, this is 107. Of course, the third group, we are looking only single bit. For your convenient purpose, we want little clarity without any confusion. If you want to look, you can prefix zeros, but you know well, if you prefix any number of bits as 0, the numerical value is ineffective. Similarly, for equivalent nibble number, the group size is 2 bits. The grouping always in the integer part from least significant bit to the most significant bit. We are having here 4 groups. For each group, we must read its equivalent nibble. The equivalent nibble here is 3, nibble here it is 1, nibble here 0, nibble here 1. So we are looking here 1013. Like this, we are having conversion of the integer part of the given binary number as hexadecimal or octal or nibble. Similarly, coming to the fractional part. For the fractional part, the grouping will start immediately after binary point. For hexadecimal case, the group size is 4. We are having here 2 groups. For each group, we must read equivalent hexadecimal value. This is 2, this is 8. This is 2, this is 8. So, for your convenience, if you want, you can suffix 3 bits as 0 to make the group size as 4. Whether we are keeping or not, default it is indication, it is a 8. For our understanding I mentioned, but without that also you must be able to speak. We are having 3 bits as 0, so that is 8. After binary point or after radix point, if you keep any number of bits as 0, then numerically it is ineffective. Hence, this is 0.28, radix point or hexadecimal 0.28. Similarly, equivalent octal number, if you look, the group size is 3 bits. We are having 2 groups. For each group, we must read its equivalent octal number. The equivalent octal number, here it is 1, here it must be 2, because while assuming there is a 0, we are looking 0, 1, 0 as 3 bit, so this is 2. Hence, similarly, equivalent nibble number, the group size is 2 bits. 3 groups we are having, it is 0, it is 2, this is 2. As said, here you can suffix 0. So there, for integer part prefixing, here suffixing. So here 0.022. You can make a cross check. It was the same result what we were looking to what we were having from the conventional work. For each one of this case, from the conventional work, we were looking to the same result. For hexadecimal, of course, we are having there 3 multiplications, so third digit is F. But here, they are having, based on the binary bits, only 2 digits. Same thing even for the octal. Of course, for this nibble number, exactly we are looking. So anyway, it is a work which is involving to convert the given binary number to hexadecimal or octal or nibble number. While looking to all these, we must take a question now. Is it possible to extend the same work, say for example, to read its equivalent radix 5 number, or to read its equivalent radix 6 number, or in general, more general way, is it possible to read its equivalent radix r number? We need to take a question like this. Based on these examples what we are having, if we take this as a question, our understanding supposed to be like this. Our understanding supposed to be like this. We are taking a case, the number is the radix of R1. This number we want to read as equivalent to radix R2. Similar to 1-to-1 correlation if we make, we are having R2 greater than R1 in all these cases. The same correlation let us make. So, we want to convert the given number which is the radix of R1 as equivalent to radix R2. Similar to this means our speaking is the grouping of the bits. Similar grouping of the bits can we do to read the equivalent radix 5 or radix 6, etc. that we are talking basically. So, coming to the general case, when the number is the radix of R1, the grouping of the digits, can we read its equivalent to radix R2? That is a question we are taking. So, for this question, while having the knowledge on these examples, we are looking first whether the radix R2 is greater than R1 or not. Suppose, if this is yes, the radix R2 is greater than R1. And further observation, if you look, further observation what we need is, it's supposed to possible for grouping, it's supposed to possible to express the radix R2 as R1 to the power of m. The similar work we want to extend with the grouping, then we are looking, the required condition is the radix R2 supposed to be read as R1 to the power of m. When radix R2 is possible to express as R1 to the power of m, if it is yes, then we are having the direct conversion. In the direct conversion, the size of the group is m. Size of the group is m. That is observation what we are having from the work. For example, while coming from the conversion of the binary number to hexadecimal, binary to octal and so, if you look, when we are converting the binary number to octal, we are not going the grouping of the 4 bits. Similarly, we are not going the grouping of the 4 bits. We are going the grouping of 3 bits. Why we supposed to go with the grouping of the 3 bits? Why not 4? Why not 2? If you take the question, it is the conclusion we'll be reading from the work. The conclusion what we are having is here this is R2, this is R1. So R2 we are able to express as R1 to the power of 3. 8 possible to express to the power of 3. Based on this, we are having the M is 3, so that is the thing what we said as a group size. Hence, when we are converting the binary number to octal number, we are reading the grouping of the 3 bits. The same thing holds good other 2 cases what we are mentioning. Here this is R2, this is R1. So R1 to the power of 4. It is the reason why we are having the group size as 4 bits when we are converting the binary number to octal. Similarly, this is here R2, this is here R1. We are expressing this as R1 to the power of 2. Hence, the group size is 2 bits. Hence, we are looking first whether R2 is greater than R1 or not. If the answer is yes, R2 is greater than R1, the answer is yes. Then we are trying to look whether is it possible to express R2 as R1 to the power of M. Even for this answer is yes. Then we are looking, the work is easy. The easy work what we are having is, we are having the grouping of the M digits. In general I'm talking, we are having the work as a grouping of the M digits. The grouping of the M digits, we are converting the given number which is the radix of R1 to R2. But consider, if this is true, it is true, it's a work. But let us consider, it may not be the case. It's the first check, it is the second check. So in the second check, there is a possibility. R2 may not be possible to express as R1 to the power of M. If R2 is not possible to express as R1 to the power of M, definitely you can't go with this direct procedure. With this direct procedure, the direct procedure is a grouping of the bits, what we are talking, grouping of the digits in general. So the direct procedure not possible. When the direct procedure is not possible, then how to proceed? The procedure is similar to the conventional work. We need to convert the given number which is the radix of R1 to decimal number. We need to convert the given number which is the radix of R1 to decimal number. How to convert the given number which is the radix of R1 to the decimal number? We know by using this polynomial equation. We are converting the given number which is the radix of R1 to the decimal number. After converting the given number which is with the radix of R1 to the decimal number, the next work is converting the decimal number to the radix R2. So how to convert the decimal number as equivalent to radix R2, that also we discuss. So we are basically having this sort of conventional work. But definitely with all our knowledge on these examples, if this is a situation, better to avoid this sort of work. For this situation, if at all we are using this sort of procedure unnecessary, we are spending time. We have to look a shortcut. The shortcut in this case, definitely the grouping of the digits in general. In this case. So based on the question need, we have to use this procedure. The question is looking with this case. The question is looking to be this case. Then definitely we should not use this procedure. If at all the question such a relation is not existing, no alternative, we supposed to go only conventional way with this lengthy procedure. But when this is possible, when this is existing, then this is a shortcut we must use. Let us try a small question. Take the question. convert the given number with a radix of 3 as equivalent to radix 9 number. Convert the given number which is the radix of 3 as equivalent radix 9 number. Convert the given number which is the radix of 3 as equivalent radix 9 number. You can take some time and you can try. So probably you might try it. If you look to the work here, the discussion what we did based on this, it is R1, it is R2. So this is true, R2 is greater than R1. Then R2 is possible to express as R1 to the power of m, we are checking. Of course, it is possible. It is possible to read R2, that is 9, as R1, that is 3 to the power of 2. Hence, the direct conversion is possible. And the group size is 2 digits. So integer part, as usual, from least significant digit to the most significant digit, the grouping we are doing. So for this 2 equivalent radix 9 number we need to read. The equivalent radix 9 number for this 2 if you look, that is 7. It is 7. So keep attention, don't get confused. This 2 is basically now with the radix of 3. When it is the radix of 3, with this polynomial equation we are looking here, this is D1, this is D0. So 3 2 ja 6 plus 1 7 is a decimal 7 basically. With the polynomial equation we are reading the decimal equivalent value. But we want here equivalent radix 9. So to read equivalent radix 9, it is to be divided with the 9. If you divide the 9, division is not possible. So that this itself 7. So if you look, whenever we are having the radix, here in this case 9, which is less than 10, when the radix is 9, which is less than 10, if the result is coming any digit here 0 to r minus 1, the result is coming any digit from 0 to r minus 1. Here 0 to r minus 1 are nothing but 0 to 6. So if the decimal value is coming any digit from 0 to r minus 1, r is 9 now, 0 1 0 1 and so on 8. So when this result is coming any digit from 0 to 8, this is straightforward equal to the radix 9 number. It is straightforward equal to the radix 9 number. It is a knowledge what we are having the number system. When I am having the number which is the radix of 9, the discretes will be only 0 to 8. It is a thing what we are looking. Say for example, the Sane number system, octal number system, the discretes are 0 to 7. If the number system is 9, the discretes will be 0 to 8. So when we are converting this number, the radix of say so and so, other than decimal, as equivalent decimal, if this result is 0 to r minus 1, in this example 0 to 8, it is nothing but equivalent straightforward to radix 9 number. If you look here, these are the things, while knowing, you will be spending less time to give the answers. So time management is very important, I said some time back. So if you look here, this will be 6, this will be 5, this will be 2. you can prefix 0. So 2, 5, 6, 7. Integer part. 2, 5, 6, 7. Coming to fractional part. So fractional part is immediately after radix point we are grouping. We are having 3 groups. For each group we must read its equivalent radix 9 number. This will be 8. This will be 5. This will be 6. You have to suffix 0 so that it is 6. Hence it is 8, 5, 6. This is equivalent radix. This is equivalent radix 9 number. It is the equivalent radix 9 number. So like this, we are having the conversion work on this example. So when we are having a question like this, it is definitely not advisable to convert as equivalent decimal, later converting as radix 9. Of course, with this work, if you try, the answer is not changing. Answer is same. But it will take some time. Objective question paper is concerned, better to avoid all this work. We are having a possibility to read directly with this knowledge what we discuss with a grouping of the digits. If you look like this, it's a shortcut, it will take less time. So like this, we must read the answers. We must read the answers. Similarly, you can have a reverse work what we did earlier. Earlier we were looking to the grouping of the digits in general. But suppose the given number we are having as like this hexadecimal number. If you want to read its equivalent binary number. When we are converting the binary number to hexadecimal number, we are bunching, we are grouping, bunching. But whenever we are converting hexadecimal to binary, it is to be expanded. It is to be expanded. So when we are converting binary to hexadecimal, bunching is the size of the 4 bits. When we are converting hexadecimal to binary, it is to be expanded to, each digit is to be expanded to 4 bits. Each digit is to be expanded to 4 bits. It's a work which is involved. Hence, we are looking here. 4 is 0, 1, 0, 0. 7 is 0, 1, 1, 1. 2 is 0, 0, 1, 0. 8 is 1, 0, 0. F is all the bits are 1. So this is equivalent binary number for this hexadecimal number. It is equivalent binary number for this hexadecimal number. So same thing we'll be doing for any other case. For given octal number, if you want to read or if you want to convert as a binary number, each octal digit is to be expanded to 3 bits and so on. If at all may not be stored in number system, something like this. Even in this case, it's the same work. If it is a given radix 9 number, if you want to look to the equivalent radix 3 number, each radix 9 digit is to be expanded to 2 digits. Each radix 9 digit is to be expanded to 2 digits. Like this, we supposed to work. So when this is a question, as equivalent radix 3, if at all we are having as a question, while giving this, the question is to read the equivalent radix 3 number. Then don't do conventionally. You expand each digit to 2 digits. So it will take less time. Let's take a question. Convert the given decimal number convert the given decimal number as equivalent binary number. As equivalent binary number. As equivalent binary number. You can take some time and you can think. So, if you tried here to read the equivalent binary number, with all this knowledge, when we are having this sort of question what we are looking is the given decimal number is with a little larger value. When the question is converting this larger decimal number as equivalent binary number, I suggest don't do direct conversion to the binary. I suggest this work don't try directly. Better convert this number as equivalent hexadecimal number. Later, try to read its equivalent binary number. It's the best thing. The best I'm talking with respect to time. The best the word I'm using is with respect to time. Definitely, if you work like this, it will take less time. But if you work like this, it will take more time. The reason you can understand with the examples what we discussed earlier. When we are converting this number as hexadecimal number, we are having only single division. Integer part I'm talking, only single division. But coming to the binary, we are having 6 divisions. We are having 6 divisions. And we are looking, when we are converting this fractional part as equivalent binary number, we did 5 multiplications to read 5 bits. We did 5 multiplications to read the 5 bits. But when you are converting this into hexadecimal form, here of course in this example we did the 3 multiplications. But these 3 multiplications are producing 12 bits. These 3 multiplication, what we are having with other example what I mentioned, it is producing 12 bits. If you want to have this number with equivalent 12 bits conventionally, then we need to go with the 12 multiplications. We need to go, if you want to read this number after binary point with the 12 bits, then we need 12 multiplications. But when you are converting this into equivalent hexadecimal number while reading after hexadecimal point 3 digits, just with 3 multiplications instead of 12 multiplications for binary direct, with the 3 multiplications we are reading the 12 bits. So definitely, as far as the time is concerned, this is the best thing. It is the best thing. Of course, for a small number, it may not be worthy to discuss. But when we are talking, the given number is very larger number. The given number, the given decimal number is very larger number. Definitely, the best thing is reading the given decimal number to the hexadecimal form, later converting that hexadecimal to binary. It's a better. So this is a suggestion I want to give. If you want to convert directly to the binary, no problem, you can do. No problem, you can do. But unnecessary, it will take time. If you do like this, it will take less time. If you try like this, the equivalent hexadecimal number here we are having as 283 3EB. If you try well, you make a cross check. By chance, if any mistake in this numerical work, rectify yourself, do the rectification yourself. If you try well, hopefully it's right. We are having here 2 divisions, so 3 digits for integer part. We are having here 3 multiplications. I think if you do any number of multiplications, the fractional part never becomes 0. So with this 3 multiplications, 3 digits we are looking. Now from this we are having the equivalent binary. The equivalent binary we are looking for each digit while reading as a 4 bits: 0, 0, 1, 0, 1, 0, 0, 0. 3 is 0, 0, 1, 1. It is for integer part. Coming to the fractional part, 3, 0, 0, 1, 1. E is 14, so 1, 1, 1, 0. B is 11, 1, 0, 1, 1. So this is equivalent binary. Just think with your own work. Conclude with your own work whether this direct conversion is better or this is better. Definitely, time is concerned, this is better. So doing this problem or insisting myself you to do this problem, the reason is just to understand which is best. So definitely you must conclude this is the best thing. Instead of doing the direct conversion, converting into hexadecimal, basically higher order hexadecimal we are doing. So converting into hexadecimal, later reading its equivalent binary, it is preferable as far as the time is concerned. After this basic work on the number system, basically our focus was conversion. After this conversion work, the next important thing in this number system is complements. In any number system, we are in need of 2 complements. One is r minus 1's complement. One is r minus 1's complement. Other is r's complement. These are the 2 complements we are having with respect to any number system. Suppose we are having a number system which is the base of 10. That is a decimal number system. In the case of decimal number system, we are having r minus 1's complement is a 9's complement and r's complement is a 10's complement. Similarly, in the case of the octal number system, r minus 1's complement is 7's complement and r's complement is 8's complement, and so on. So that in the case of the binary number system, r minus 1's complement is 1's complement and r's complement is 2's complement. So in general, with respect to any number system, we are having these two complements. One is r minus 1's complement and other is r's complement. Yes, try to speak yourself. What is the why we supposed to learn these complements with respect to number system? What is the importance of learning these complements in the number system? What is the concern to learn these complements with respect to any number system? When we are taking this as a question, why we are learning these complements in any number system, based on little knowledge what you might be learned in the college, you supposed to give the answer. These complements were in need in any number system, basically to simplify the subtraction operation. The concern to learn these complements in any number system is basically to simplify the subtraction operation. I can quote an example, probably many of you are having idea. Like learning maybe CO subject or microcontrollers or microprocessor subject, you might come across even the digital logic also in the college, you might come across. When we are having the subtraction of the binary number B from binary number A, the subtraction we prefer to do as A plus either maybe 1's complement of B or A plus 2's complement of B. So, some hardware, if at all where ready hardware is available to perform addition on two binary numbers, a ready hardware is available to perform addition on binary number X and Y. The hardware which is performing X plus Y operation can be used with a little additional hardware to perform subtraction of the binary number B from A. So to perform the subtraction operation of the subtraction operation, that is subtracting of the binary number B from A minus B operation, we are looking this is either maybe A plus 1's complement of B or A plus 2's complement of B. So once it is A plus 1's complement of B or A plus 2's complement of B, as hardware point of view, it is as good as adding two binary numbers. So the hardware what we are having to perform addition on two binary numbers X and Y, that can be used with a little additional hardware. The additional hardware what we need is just to perform the complement operation, we need little additional hardware. There is a comfort, that is a convenient what we are having. The subtraction is with the help of these complements is converted as addition. So basically, the purpose of learning these complements in any number system is to simplify the subtraction operation. Now let's look how we are reading r minus 1's complement. Let us read first this. To read r minus 1's complement of the given number, to read r minus 1's complement of the given number, we are subtracting every digit of the given number from r minus 1. While subtracting every digit of the given number from r minus 1, we are having the result. This result is r minus 1's complement. So that to read the 9's complement of the given decimal number, we are subtracting every digit of the given decimal number from 9. To read 7's complement of the given octal number, we are subtracting every digit of the given octal number from 7, and so on. So these are the this is the procedure what we are having to read in general r minus 1's complement of the given number. Coming to r's complement. To read r's complement of the given number, we are adding 1 to rightmost digit. We are adding 1 to rightmost digit of r minus 1's complement. To read r's complement to the given number, we are adding 1 to the rightmost digit of r minus 1's complement. So with this, the result we are reading as r's complement. So for the given decimal number, if you want to read 10's complement is r's complement on the decimal number. We are adding 1 to the result of 9's complement. Similarly, to read 8's complement to the given octal number, we are adding 1 to the result of 7's complement, and so on. So these are the procedures which are involving in general to read r minus 1's complement and r's complement of the given number. Let's try for a small question. Let's take the question. Find 6 complement of the given number. The question is, find 6 complement of the given number. Find the 6 complement of the given number. You may be looking some options in the ABCDs as like this. Some options may be having like this. While looking to this question, from the given options, we must be in a position to eliminate the option A and option B. We must be in a position to eliminate option A and option B. We'll talk a little later how we are eliminating. But definitely we should not answer either this A or B. If you look here, how we are doing this work. So we must read 5's complement of this given number first. To read the 5's complement of the given number, each digit of the given number is to be subtracted from 5. While subtracting each digit of the given number from 5, we are having here, it is 5, this is 2, this is 1, this is 3. Later, to read the 6's complement of the given number, we are adding 1 to the rightmost digit of the 5's complement. We are adding 1 to the rightmost digit of the 5's complement. While adding 1 to the rightmost digit of the 5's complement, the result what we are looking is, say, randomly I am talking, 5 plus 1 is 6. So, by looking this as 6, you need to have a question, something going wrong. How we are concluding something going wrong? While looking to this radix, we are speaking something going wrong. Because when the number system is the radix of 6, the possible discretes will be 0 to 5. When the number system is the radix of 6, the possible discretes will be only 0 to 5. So it is observation what we are having from all the work what we learned. When we are having the discretes, whenever we are having a radixes, or the discretes will be 0 to r minus 1. I am not teaching any new. It's the one what we are having with all our knowledge on the standard number system. Hence, when we are looking to the radix is 6, the discretes are 0, 1, 2, 3, 4 and 5. Hence, what is the answer we are giving That answer must be just by using only these digits. The answer must be using only these digits. By chance, in the options we are having any option other than using these digits, any option we are having using other than these digits, definitely that is not the answer. So that is the reason, or based on this reason, I said while looking to these options, without any sort of work, we are having possibility to eliminate the option A and option B. By chance, in the given ABCD options, we are having out of 3 options are like this, other than these digits, at least one digit is other than these digits, then definitely all the 3 options you must cut. So once we are eliminating all 3 options, the remaining leftover only one, of course, that's supposed to be the answer. So like this, sometimes with the common sense, we need to work with the elimination procedure. And truly speaking, this decimal 6, when we want to represent as a radix 6, the answer must be this. Similarly, the decimal 7, when we want to represent the radix 6, the answer is 1, 1. Decimal 9, if you look, the answer is 1, 3. The answer is 1, 3. So, and so on, any other case. So it is observation. With all these cases, if any doubt you are having, go with the expansion work, the polynomial equation. In all these cases, D1 is this, D0 is this, you can work out and you can verify. So let us come to this now. So while reading this is a 6, as I said, you need to have a doubt. You are getting a doubt. Then the next question is arise. How to read the right answer? The next question arise. How to read the right answer? The answer to this, how to read the right answer, for this, the answer is, you need to adopt the procedure what we are having in the decimal number here also. We must adopt the same procedure what we are having in the decimal number system, even here or in general for any radix based number system other than 10. Say for example, we are having a decimal number as 620. For this decimal number, we are interested to read its tens complement. To read the tens complement, we are reading first ninth complement of this number. The ninth complement of this number we are reading while subtracting every digit from 9. While subtracting every digit from 9, we are having this is 379. Later, to read the to read the tens complement of this number, we are adding 1 to the rightmost digit. While adding 1 to the rightmost digit, we are having very familiarity with this decimal number system. Without any mistake, we will be speaking the answers. So 9 plus 1, we are keeping here 0 and we are forwarding carry to the next significant place. But we need to understand conceptually, when we are forwarding carry, when we are not forwarding carry, that we need to understand. We are forwarding carry to the 10 to the power of 1's place from this 10 to the power of 0's place. So that I said we are forwarding a carry to the next significant place. With all our knowledge on the decimal number system, you know, whenever we are adding 2 digits, if the result, whenever we are adding 2 digits, if the result is coming greater than or equal to the radix, if the result is greater than or equal to the radix, then we are forwarding a carry to the next significant place. After forwarding carry to the next significant place, at the corresponding significant place, the digit what we are reading is, we are subtracting radix from this result. What is the result we are getting? This is to be placed here. It is to be placed here. So in this example, the result is 10. 9 plus 1, 10. We are subtracting radix. Radix is 10. The result is, of course, 0. It is the reason why we are having here 0. So whenever the result is greater than or equal to the radix, first we are forwarding carry to the next significant place, and to identify the digit at the corresponding significant place, we are subtracting the radix from the result that we are placing here. So it's a procedure. I said I am not talking any new. It's a very much it is known to you, but the known thing you need to adopt well properly. That is important here. Say for example, I'm having a number 76, other number is say 58. So for these decimal numbers, when we are having this addition, so 6 plus 8, 14. 14 is greater than the radix of the number system. Hence, we are forwarding carry to the next significant place. We are performing the addition at the units place. Next significant place is 10 to the power of 1's place. Now, what is the result we are looking? The result is happened to be 14. To read here the digit, we are subtracting from this result the radix. The radix is 10. So this is 4. It is the reason why we are having here 4. And of course, the answer is not our concern here. The answer is not our concern. Our concern is looking to the procedure. Same thing here also. The decimal number system, what we considered here, if you look, of course, it is the answer. But our concern, as I said, not for this work. Our concern is looking to the procedure here. So based on this, we are looking here. Coming to this number, 5 plus 1 is 6. So the result what we are having, the result is 6. Once the result is 6, we are forwarding a carry to the next significant place. The next significant place is 6 to the power of 1's place. After forwarding a carry to the next significant place, from this result we are subtracting radix. So subtracting radix is nothing but subtracting 6 here. It is giving 0. Hence, we need to place here 0. And of course, here this is 3, this is 1, this is 3. Hence, answer to this question is option C. The answer to this question is option C. If this is a question in the exam paper, take it grant. 80% students will be giving answer as option A. 80% students will be giving answer as A. They are giving answer as option A. It is not like that they don't know the subject, they don't know knowledge. It is not like that. The mistakes the students are in general as a human being, even sometimes maybe me. As a human being, when we are doing the mistake is, we'll be doing few of the things, take it grant way most of the times. Few things as a, getting a feel as a easy, while looking this sort of question, initial understanding what you'll be looking is question is easy, that feel you will be getting. With that feeling, you'll be looking to the answer, take it easy way. So while looking to the answer, that take it easy way, most probably majority of the students will be answering the option A. And you may not be recognizing what went wrong also. While looking to such sort of few questions, after completing exam, when you are sharing your opinion on the exam paper with your friends, you may give your opinion, the paper is easy, the question paper not worthy paper. Such comments generally we make. But of course, it is not correct. When you are getting an idea on any question, such easy feeling, simple feeling, my suggestion is, as far as the particular GATE exam is concerned, very tricky thing. Conceptual questions will be there. Few questions, not every question. So when you are having such a feeling as easy or simple, better read the question once again. Better look to the solution once again. Always it is better. It's better. So while keeping these things in the mind, you may not do the mistakes when we are having such simple questions. We are doing the mistakes on the simple questions, as I said already, because of our nature of take it easy way, looking as simple. Okay, answer for this question is option C. Let us discuss one more question. Again, a concept-based question. Note down. What is the sum of the given two hexadecimal numbers? What is the sum of the given two hexadecimal numbers? What is the sum of the given two hexadecimal numbers? The given two hexadecimal numbers are 7CBD, one number, other number is 4AE8. So just take some time and try. The meantime, I will work little later. So when we are having this as a question, most of the times what we are doing is we are converting these numbers to decimal or maybe converting these numbers to binary form. Later we are adding say these decimal numbers or say these binary numbers. Finally we'll be looking back to equivalent hexadecimal number. It is the practice generally we are having. Of course, the work what we are looking here 100% correct. There is nothing wrong here. Work is concerned 100% correct, nothing wrong here. But with all the knowledge on the number system what we learned, we are having possibility to eliminate this lengthy work. We are having possibility of eliminating this lengthy work. We can add these two hexadecimal numbers as similar as adding of two decimal numbers. We can add these two decimal numbers as similar as simple adding of two decimal numbers. That procedure possible to adopt. It is possible. So if we adopt like that, definitely we'll be spending less time to answer. So let's try here directly. At 16 to the power of zeros place, we are having the digits. The digits are D and E. So D plus E. D in the hexadecimal, D is 13. D is 13, E is 14. So 13 plus 14, 13 plus 14 is 27. 13 plus 14 is 27. So we are looking here, this 27 is greater than the radix, where the radix is 16. If any numerical wrong I am speaking, do yourself later. So D is 13, E is 14. So 13 plus 14, it is 27. 27 is greater than the radix of the number system. Hence, we are forwarding a carry to the next significant place, that is 16 to the power of 1's place. That is 16 to the power of 1's place. And from this result, we are subtracting radix. Radix is 16. While subtracting 16 from this, it is 11. And of course, this 11 in the hexadecimal number system, we are representing as B. Coming to the 16 to the power of 1's place, B plus 1, it is C. So C is 12. 12 plus 8, 20. Again, we are looking, this 20 is greater than the radix of the number system. Hence, we are subtracting radix from this. While subtracting radix from this, it is 40. It is 4. 4 we are placing at the corresponding significant place. And of course, we are forwarding carry to the 16 to the power of 2's place. We are having addition at 16 to the power of 1's place. So the next significant place is 16 to the power of 2's place. Coming to this, C plus 1 is a D. So D is 13. So 13 plus A is 10. 13 plus A, 13 plus 10 is 23. Again, it is greater than the radix of the number system. Once it is greater than the radix of the number system, we are forwarding a carry to the next significant place, that is 16 to the power of 3's place. From this result, we must subtract radix, that is 16. So we are having at the corresponding significant place, we are reading as 7. 7 plus 1, 8. 8 plus 4, 12. 12 we are reading as a C. Hence, this is the answer. As said, if any numerical mistake is happening, rectify yourself, try work. So importance is the knowing the procedure. So hopefully it is right. D is 13, E is 14. So 13 plus 14, it is 27. So we forwarded carry to the next significant place. From the 27, we subtracted 16, that is 11. 11 is B. Coming to this, B plus 1 C. So C is 12. 12 plus 8, 20. So we forwarded carry to the next significant place. From the 20, subtracting 16, it is 4. C plus 1 D. So D is 13. 13 plus 10 is 23. So we forwarded carry to the next significant place. From the 23, while subtracting 16, it is 7. 7 plus 1, 8. 8 plus 4, 12. 12 is C in the hexadecimal. So that it is the answer. So like this, we are working. But instead of this, I said, if at all we are looking conventionally like this, definitely we are spending less time. We need to spend more time. So possible for us to eliminate. So this sort of thing, not only in the hexadecimal case, in general, for any number system, when we come across this sort of thing, we are having possibility to use. We are having possibility to use. So like this, we are working, adding of two numbers which are with a radix other than 10, with a higher numerical values or lower maybe other than the 10, the more digits if at all we are having. Instead of going conventional way, I suggest better work like this.